Hello. Last time I was talking about Unit 7, that's about solvent extraction and colligative properties. So we completed the part related to uh, solvent extraction, and now we are going to talk about colligative properties. So the main objectives for this part of the unity is to describe the meaning of colligative properties, then to determine the molar mass of a given substance by using the boiling point elevation, freezing point elevation, freezing point depression, and osmotic pressure. Their main four colligative properties: boiling point elevation, freezing point depression, vapor pressure lowering, and osmotic pressure. What are colligative properties? Colligative properties are those properties bound together by a common origin, which means that they all depend on the same thing. They all depend on the number of solute particles present in solution. Particles, I mean atoms, ions, or molecules. So they don't depend on the identity of the solute, which means that they don't depend on the type of the solute. Any type of solute leads to the same property. Let's start by looking at what is the boiling point elevation. First of all, what is boiling point? Boiling point is the temperature at which a liquid changes into vapors at a constant pressure. So this happens when the vapor pressure of that liquid equals to the atmospheric pressure if this boiling is carried out in an open container. So let's take an example for us to understand what is the boiling point elevation. Elevation, to elevate, means to increase. So here the idea is that when a solute is added to a given solvent, the boiling point of that solvent increases. Here we have an experimental data that gives us what changes happens when salt is added to water. So the boiling point of pure water is 100 degrees Celsius at 1 atmosphere. But when 1 mole of sodium chloride as a solute is added to 1 liter of water, we have 1 molar solution, and then the boiling point changes to 101 degrees Celsius. This is at 1 atmosphere. So as you can see, the boiling point has increased by 1 unit. Then we are asking ourselves, why? Why is this changing in this way? Actually, when you look at what we have here, is that the addition of a solute molecules increases the attraction of solvent molecules, which prevent them from escaping to the liquid phase. Before, molecules of water were interacting by hydrogen bonds. But when you add like sodium chloride releases ions, and these ions also attract the molecules of water. That attraction caused by the ions released by the solute added, they attract molecules of water and prevent them from escaping the liquid phase, which means that for it to boil, it requires more energy. That's why the temperature is higher. Another reason is that when the solute particles are added to a given solvent, actually they occupy a space on the surface of the liquid which hinders the vaporization of the solvent molecules. In all these reasons that I have given, you understand that the presence of the solute particles makes the boiling of a given liquid harder than it was before. So this property of boiling point elevation can be quantified. So meaning that you can determine it experimentally, or you can calculate it depending on the experimental data that you are given. So how do you find the boiling point elevation? So if the value of the boiling point of the solution is given and the value of the boiling point of the solvent is given, you just calculate the difference, which means that delta B equals to TB minus T naught B, which means that delta B is the boiling point elevation, and then TB is the boiling point of the solution, and then T naught B is the boiling point elevation for the pure solvent. So here we are asked, why do we take the boiling point of the solution minus the boiling point of the pure solvent, not the boiling point of the pure solvent minus the boiling point of the solution? It's because the boiling point of the solution is higher than the boiling point of the solvent. You take the bigger value minus the smaller value. So since this is a colligative property, and we have seen that colligative properties are those properties which depend on the number of solute particles, the boiling point elevation is also proportional to the molarity of the solute in the solution. Molarity here, I mean the concentration. The concentration expresses the amount of the solute that is present in the solution. So the formula is this one. The boiling point elevation delta B equals to I times M times KB. What is I? I is the Van 't Hoff factor that I will explain later. Then M, small m, this is the molarity. Molarity, which is different from molar concentration. This is given by the number of moles of the solute per kilogram of the solvent. That's the mass of the solvent expressed in a kilogram. That's how it is calculated. Then Kb is the molar boiling point elevation constant, which is a constant of proportionality that depends on the type of the solvent that you are dealing with. So by definition, we have seen that the boiling point elevation is the increase in boiling point of the solvent when a solute is added to it at a given pressure. That's delta B. Van 't Hoff factor I is a constant associated with the amount of dissociation of the solute in the solvent. How do you get to know the Van 't Hoff factor for a given solute? For substances, for solids which do not dissociate in water, these are non-electrolytes or non-ionizing solutes, such as sugar, alcohols, aldehydes, ketones. All those ones, they don't split into ions when they are put in water, meaning that when you put one molecule of the solute in water, there is only one particle. That's the reason why the Van 't Hoff factor for this non-ionizing, non-electrolyte solute is always equal to 1. For solutes that completely dissociate into ions, these are strong electrolytes, the Van 't Hoff factor depends on the number of the ions that 1 mole of that substance releases in water. I'll give an example to make it more clear. Sodium chloride as an electrolyte, this is an ionic compound. When it's put in water, for example, it dissociates into 2 ions. These are sodium ion and chloride ion. So if you count the number of particles that are released by one compound, 1 mole of the compound is 2. Now the Van 't Hoff factor is equal to 2 for sodium chloride. For iron 3 chloride, 1/4 compound, 1 mole of the compound releases iron 3, which is one positive ion and 3 negative ions. These are chloride ions. Total number of particles released by 1 mole of the compound is equal to 4. The Van 't Hoff factor is equal to 4 for iron 3 chloride. I guess that with these examples, you understand how you can also determine the value of the Van 't Hoff factor for a given compound. Let's take some examples to see how these formulas that we have been talking about can be applied in the calculation for a given problem. We are given that the boiling point of pure benzene is 80.1 degrees Celsius and its boiling point elevation constant Kb is equal to 2.53 degrees Celsius per molar when 10 grams of non-volatile and non-ionizing solute is dissolved in 200 grams of benzene. The resulting solution boils at temperature of 81.2 degrees Celsius. Find the molar mass of the solute. To solve this, we have first of all to remember that the boiling point elevation is given by the difference between the boiling point of the solution minus the boiling point of the pure solvent. We have all those values in the question. So let's apply them, substitute them in the formula, then we get the 81.2 degrees Celsius minus 80.1 degrees Celsius equals to 1.1 degrees Celsius. This is the boiling point elevation. We also know that the boiling point elevation can be found by taking the Van 't Hoff factor times molarity, which is equal to the number of moles per mass of the solvent in a kilogram times Kb. We have everything, but we don't have the number of moles. So let's solve for the number of moles. We substitute all values and then we solve for the number of moles. We find that the number of moles equals to 1.1 times 0.2 divided by 1 times 2.53, and then we find the number of moles that is equal to 0.0869 moles. After finding the number of moles, we can find the molar mass of the solute that we are asked to find. Molar mass is given by the mass of the solute in grams per number of moles of that solute. We have already found the number of moles previously, and now we are going to substitute values and we get 10 grams, that's the mass of the solute that was dissolved, divide by 0.0869 mole. This is the number of moles we have just found. Then we find the molar mass that's equal to 115.07 gram per mole. Worked example number 2. We are given 31.65 grams of sodium chloride, which is added to 220 milliliters of water at 34 degrees Celsius. Given the boiling point of pure water, there is 100 degrees Celsius, and its boiling point elevation constant is equal to 0.51 degrees Celsius kilogram per mole. How will this affect the boiling point of water? So we are asked to find the boiling point elevation. The boiling point elevation is found by taking the Van 't Hoff factor times molarity times Kb. So if we use the formula for finding molarity, molarity again is equal to number of moles per, okay, is found, molarity is found by taking number of moles of the solute in grams divided by the mass of the solute in kilogram. But the number of moles is also equal to mass of the solute divided by the molar mass. So if we combine those formulas in the above formula, we can find the new formula, which is this one, the one we have here, this one. So as you can see, is that molarity is given by the number of moles. Number of moles is given by mass over molar mass, okay, per mass of the solvent in a kilogram. All these give molarity. Yeah. Then we can substitute the values into this formula that we have, this new formula that we have introduced. So for sodium chloride, since it is split into two ions, sodium ion and chloride ions, the Van 't Hoff factor is equal to 2. Then times the mass of the solute, that is 31.65 grams. Then times 0.51, that's the boiling point elevation constant, it's given the question, and then divided by the molar mass of sodium chloride that we can find, and it's equal to 58.44 gram per mole. Then times the mass of the solvent that is converted into kilogram, and then we find the boiling point elevation that is equal to 2.53 degrees Celsius. The boiling point elevation of water was raised by 2.53 degrees Celsius and was changed from 100 degrees Celsius to 102.53 degrees Celsius. That's all. Thank you very much. We shall come next when we are talking about other colligative properties. Thank you.